definite integral between x and b by counting squares. Now, this will be the first time that we've really talked about definite integrals, but we're really going to hammer them today, tomorrow, next week. I think this might be the only section that really introduces it. Yep. But there's two pieces of it. This first piece is kind of estimating by hand, and then the second 2 pages that we're going to talk about the next time is estimating with a calculator, but doing the same sort of thing. Alright, so let's start reading together. A few sections ago we estimated the derivative of a function, which is the instantaneous rate of change of y with respect to x. So, again, connecting that a derivative represents an instantaneous rate of change. In this section, we'll learn about one type of integral, the definite integral. So we've kind of done a brief introduction of derivatives, which is one branch of calculus, and then we're going to do the other branch foundation right now. Alright, so suppose you're driving your car. The velocity increases for a while, then levels off, and we're going to draw a sketch of a graph showing the velocity increasing from 0, then approaching and leveling off at 60 feet per second. Now what you have to know in this graph is that the y-axis here represents velocity. So we're going to label that velocity in terms of time, feet per second. And maybe we even include those units, feet per second. And then the x-axis here is going to be time. And the time is going to be in seconds there. Alright, and so in this situation, we're supposed to draw something that shows that velocity increasing to a specific time and then leveling off. Now I'm going to make this a little bit more specific. Mark 10 points here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We know that it wants us to level off at 60, so 1, 2, 3, 4, 5, 6. Draw a little dashed line there. That's 60. This is going to be 100 seconds. I want you to mark the 30-second mark and the 70-second mark. Okay. We're going to increase to about 30 seconds. And around 30 seconds, that's going to be where it starts to level off. And then you kind of show the leveling off portion here. And did it just say, no. Okay. We have 2 regions of area here underneath the curve. You have this section here where the top of the curve is changing the whole time. And then you have up here where it levels off, you could even think of that as a square. Right? So when it actually levels off, your velocity is constant. You're going 60 feet per second consistently. Where the velocity is changing dramatically is this first section between 0 and 30 seconds. Then, what else did I want to say here? And then you have this in-between section where probably part of it is almost leveled off. It's not changing as dramatically as the first part, but you can still see that the top portion of this is not necessarily a straight line. So describing these parts of the graph, we would say velocity is changing quickly from 0 to 30, starting to level off between 30 and 70, leveled off at 70 to 100. How can we find the distance traveled using this graph? way back in Algebra 1, we did some work with this formula. Distance, I called it the dirt formula because it kind of looks like the word dirt. But distance equals the rate times the time. Okay, so I just want to look at this object here. If we looked at that as a shape, because it is, if that's a straight line up here to show that it's leveled off, it would be a rectangle, right? Well, the distance is the rate times the time. Well, my y-axis is the rate, or represents the rate. My x-axis is the time. So this is telling me if I multiply my rate times my time, I get my distance. That makes sense. If you're going 30 miles per 1 hour and you travel for 3 hours, how do you figure out how far you go? Well, you multiply them together, hours cancel, and you end up getting 90 miles. That's what we're going to be doing here. You're multiplying your rate, which in this case represents your y-axis, times your time. Or really, aren't you just finding the area of that shape there, which in this case is a rectangle? So we could say between 70 and 100, if he's going consistent, or you're going a consistent speed of 60 feet per second, to find how far you went, wouldn't you multiply 60 feet per 1 second times 30 seconds? Seconds cancel, you get 60 times 30, which would give you 1800. It not only gives you the area of the rectangle, but that means something in this case because the y-axis is a rate and the x-axis is a time. Okay, so how can we find the distance traveled using this graph? You can find the distance by multiplying rate times time. With a graph, you can estimate the distance traveled by finding areas under the curve and adding them up. Qualifier there is the y-axis must be rate, x-axis must be time, so d equals r times t is true. Meaning basically like just finding the areas underneath the curve. If this was just some other value, like if this just was miles but not miles per second, when you multiply miles times second, you're getting the rate. But if your y-axis is the rate already, when you multiply rate times time, times cancel, leaving you with just the distance traveled. Okay. Now, this part of the graph was really easy to find. However, this part is changing, and this part is changing. It's not a straight line up here to find the distance traveled between 30 and 70 seconds, and it's not a straight shape here. I mean, there's some curvature there, even though I can show you another graph that looks really, that's going to be sideways, but oh goodness, maybe not. Okay, so like that graph right there, you can see the three distinct portions, but you can see how curved that is. That isn't a nice shape. And then it's close to being rectangle there, but it's not quite. So when you have changing velocity or changing rates, we have to do something. We have to estimate a little bit differently than just straight finding areas, big chunks of area underneath the curve. So you're going to take like chunks of area, and we're going to actually narrow in a little bit to find the distance traveled. The process of evaluating a product in which one factor varies, so in this case, that would be velocity varying, is called finding a definite integral. We're going to obviously more and more get into what an integral is and what it means. Derivative was finding the instantaneous rate of change, or the velocity, really. Integration is, or finding the integral, is basically multiplying when one of the things you're multiplying changes. So like in this case here, velocity is what's changing. Time isn't changing. I mean, it's increasing, but it's not fluctuating like crazy. It's going forward at a constant rate. Where in this case, the y value is changing, not at a constant rate. That would be a line, but it's changing every moment. You're at a different point. You're not forming a nice geometric shape underneath the curve. Alright, so we're going to look at two examples here. Oh, and I just shut my book. Hold on just a second. And you will need a calculator, so as I'm looking this up, make sure you find a calculator somewhere. Here we go. Oh, no. Here we go. Okay, so we're going to evaluate the definite integral of f of x equals 8 times 0.7 to the x from x equals 1 to x equals 7. Alright, now the first thing I'm going to do is on the calculator, I'm going to go ahead and graph this to see what it looks like. So 8 times 0.7 to the x. I'm going to change my window to be a little more friendly. So from negative 10 to 10 in all cases. And then I'm going to hit graph. Okay, I'm going to zoom in. Obviously what I want to look at is in that first quadrant there. So I'm going to zoom in a little bit. Oh, that's too much. I'm going to go to my zoom button. Come on. Oh, sorry, not zoom, window. Let's go from 0 to 10 and from, I don't know, 0 to 10. And it just gives me the first quadrant there. I'm going to go ahead and sketch that. So I want 10 tick marks. I'm not even sure how to space that out. But you don't have to be perfect here. I just want, because we're going to do all the work on the calculator, I just want kind of a graph of what this looks like. Okay, so the definite integral. At this point, what you need to know about the definite integral is that it's the area under the curve. We looked at the connection with if you already know the function represents a velocity, and that's the y values are your velocity, then the area underneath the curve means distance. But when you're just talking about straight definite integral, you're talking about multiplying, and it's always to try to find the area underneath the curve. We're looking for the area underneath the curve, excuse me, between 1 and, what do we say, 7? So I'm going to narrow my window even more. This is kind of the process that you're going to have to go through, the practice problems we do tomorrow. I'm going to go from 1 to 7. So I'm going to narrow my x-axis to be exactly the area that they're looking for. I'm going to adjust one more time. Well, no, I think I'm going to adjust one more time. I'm going to go from 0 to 7 there, just to space it out a little bit more. You want a pretty good picture of this graph. You don't want it too small, because what we're going to do next. Next, you're going to go to Format, which is under the Zoom, and you want to turn your grid on. then when you go to graph, you're going to see all these little squares pop up. Now, we're going to mark each one of these squares as an area. So in this case, since all my tick marks go up by 1 on both the x-axis and the y-axis, every unit on this screen is worth an area of 1. I'm going to basically use the grid feature of my calculator to estimate the area by counting up all of the little squares underneath the area and adding up all their areas. So I'm going to talk kind of through the process of what I do here. And I need actually a dry erase. That's not a dry erase. Here we go. Nope, that's not a dry erase. All I have are Sharpies. What in the world? Oh dear. I don't know. Hold on a second. Alright. Come on. Okay. Usually this is what I do. I go through and I count all of the boxes. So any whole boxes that are underneath the curve, I count. I would count that box right there as 1. And actually I'm going to zoom in a little bit so you get a better picture here. Okay. So I have 1, 2, 3, 4, 5, 6, 7. I'll count that box as a whole one. 8, 9, 10. So I'm going to list all the whole boxes I have. So I have 10 whole. And then I'm going to list all my partial. Now when I list my partial, and actually let's do this different. Let's say instead of saying 10 whole, I'm going to count up all my whole ones and then actually multiply it by the amount of area that one square is worth. Because sometimes your tick marks will be different. So maybe you went up by 2's on the y-axis, so then actually every box is worth 2. You want to make sure that you're careful there to make that connection. So that's why I label my little area box over here to represent how much each square is worth. I have 10 whole squares at 1. And then I'm going to add up all my partials. So looking at this little piece here, whoops, okay, so underneath the curve, I have this little piece here, and part of that whole square, I might say that's 0.2. Okay, so I'm going to write on my paper 0.2 times 1. Then my next one here, maybe that's 0.6 of the whole area there. Next one here, maybe that's 0.3. Next one here, maybe that's 0.9. Next one here, maybe another 0.3. Next one here, that looks to be about 0.5 maybe 0.6. That one, barely there, so maybe that's 0.1. Then my last little area box, maybe I do 0.7. Okay? Now, again, this isn't an exact science. That's why you want a really good window, because you want to make sure that it's easy to see your boxes and easy to see where the partials are. I think I covered all of them. And then basically what you do once you have determined your partials and your whole boxes, you write them all out, and then we're going to add them up. So, going back to your calculator, I'm going to erase all of that. Okay. So you're going to add up 10. Now, because each one of these is just times 1, I'm just going to add up the 10, the 0.2, and the 0.6. 13.6. So we would say, based on this, definite integral integral is 13.6 square unit. So that will be 13.6, yeah, 13.6. So that would be basically how you do this type of problem, and this is very basic. I mean, there's easier ways to do it than just counting boxes, but if you just need to estimate the product where one factor varies, then graphing, getting a good picture of your graph for the piece of area that they want, and then counting boxes and counting up all the areas of the boxes, that will give you a pretty darn good estimate. Okay, we're going to do the same type of thing again for example 2, just with a different function. First, I shut my book again. I'll have to look it up. Okay, the second function that we're going to look at, we're going to be a little bit more specific. We have a velocity function here. So it's going to be negative 100t squared plus 90t plus 14. That means in this scenario here, and I'm going to make this the first quadrant again, my x-axis is time, seconds, and my y-axis is velocity values. Mark a 10, a 20. I've already graphed this to hopefully alleviate some of the time here. 10, 20, and 30. And then mark that as 1. And then halfway in between is 0.5. Doesn't have to be perfect. It wants, or I'm telling you, that we're supposed to estimate the definite integral from t equals 0.1 to t equals 1. Oh, I'm sorry, this is in feet per second. What you're going to notice here is because this is a velocity function, when we find the area underneath the curve, oh, and just so you know, we're not going to, well, never mind, we're going to graph that. When we find the area underneath the curve, the other thing it's going to represent is how far this object has traveled. Because you're multiplying a rate and a time together, the result is always a distance type answer. Okay, so now to graph it. Negative 100 t squared plus 90t plus, 90x plus 14. Window, I want you to adjust from 0.1 to 1, and we're going to go up by 0.1. So every tick mark is going to be worth 0.1. And then we're going to make the y-axis go up to 50. Okay. Okay, now you'll see on your calculator, at least on mine, it doesn't give me nice little boxes, which means I have to adjust my window a little bit. Instead of going up by 1, maybe I go up by 5. Okay, so now it's giving me some grids. So you just change the scale a little bit until you get some grids. And this is where we draw the little area box to represent what each square is worth. Every x, like I went up by 0.1 on my x's, so every x is worth 0.1. And then every y is worth 5. So 5 times 0.1 will give me an area of 0.5. So every square is worth an area of 0.5. Okay, going back to the graph. We're going to go through and we're going to count up how many holes we have, and then we're going to count our partials. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 39. Okay, so we have 39 holes. So 39 times 0.5. And then we're going to figure out all my partials. So again, I'm going to kind of do it up on the side, but we're going to look through it here. Let me zoom in a little bit. Okay. All right. This looks like a 0.8 maybe, plus a 0.9, plus a 0.5. So 0.8, 0.9, 0.5. Okay. This looks like, well, I might count that as another hole, so 40. It's really close. Maybe that's a 0.6. Maybe that's a 0.9 of the square. Maybe that's a 0.8. And this one looks like a 0.5. This one maybe is a 0.9. This one maybe is a 0.1. And then this last partial I might say is a 0.6. Okay, so I got all my holes and all my partials. Here's my list that I have going here. And I should at least draw on my curve. I don't know. Just draw a curve there. Alright, so area. Alright, so I'm going to add up all of those values. Now, what you could do is you could just add 40 plus 0.8 plus 0.9 plus add up all those and then just multiply it once by 0.5. That would be perfectly fine, and that's what actually I'm going to do here. So 40 plus 0.8 plus 0.9 plus 0.5 plus 0.6 plus 0.9 plus 0.8 plus 0.5 plus 0.9 plus 0.1 plus 0.6. Multiply that by 0.5 and you end up getting 23.3. So the definite integral, is 23.3 units squared. Well, actually, in this case, since we have units, it's going to be feet, because you're multiplying all your feet per seconds by seconds. The seconds will cancel, just leaving you with feet. Okay, so we're going to really practice that tomorrow, but you're done with notes for today.